Using Apple frameworks, e.g. UIKit, Foundation. UIKit is one of the key Apple frameworks used for building user interfaces in iOS, tvOS, and watchOS apps. It provides a wide range of classes and protocols for laying out and managing the application's visual elements. In the code snippet, we start by importing the UIKit framework, which allows us to access its classes and methods. We then create an instance of UI label, which is a UIKit component for displaying a small amount of text. We set the text of the label to Welcome to UIKit and align it to the center. This label can be added to your app's view to be displayed on the screen. Networking with URLSession. Swift's URLSession class provides a rich set of APIs for networking, allowing you to interact with RESTful web services. Performing a GET request is one of the most common operations in web networking, where you retrieve data from a specific endpoint. The code snippet defines a simple GET request using URLSession's dataTask method. First, it creates a URL instance. Then, it initializes a dataTask with a closure that handles the completion of the request. Inside the closure, the error is checked, followed by the status code of the HTTP response to ensure it's within the 200 to 299 range, indicating a successful request. If data is received, it's converted to a string and printed out. Finally, task.resume starts the networking task. JSON parsing and serialization. JSON parsing and serialization refers to converting JSON data into Swift objects and vice versa. Swift uses the codable protocol to define types that are encodable and decodable, which simplifies working with JSON. Serialization converts a Swift object into JSON, and parsing converts JSON back into a Swift object. The code defines a struct named user that conforms to the codable protocol, allowing it to be encoded and decoded with JSON. It then creates a JSON string, converts that to data, and uses JSON decoder to parse the JSON and initialize an instance of the user struct. If parsing is successful, it prints the user object. Otherwise, it prints an error. Working with databases, e.g. CoreData, SQLite. CoreData is a framework provided by Apple for iOS and macOS for data persistence. It allows you to model your data at a high level, create objects which are instances of NS-managed object, and manage an object graph. CoreData takes care of object lifecycle, object graph management, and persistence to a store like SQLite. Below is an example of how to set up a simple CoreData stack and insert a new object into the database. In the code provided, we import CoreData and then access the persistent container from the app delegate, which encapsulates the CoreData stack. Then we create a new NS-managed object instance using the entity description for the entity person. We set the name and age attributes on the person object. Finally, we try to save our managed object context to persist the new person object. Error handling is done with a do-catch block to catch any errors thrown during the save process. Third-party dependency management, e.g. CocoaPods, Swift Package Manager. Third-party dependency managers are tools that help developers incorporate external libraries or frameworks into their projects. They handle downloading, updating, and configuring these dependencies to streamline the development process. CocoaPods and Swift Package Manager are popular choices in the Swift ecosystem. This line of code demonstrates how to import a third-party library, Alchemy, after it has been added to a Swift project. Alchemy would typically be added via a dependency manager like CocoaPods by including it in the pod file, or with Swift Package Manager by adding it to the package.swift file. The dependency manager takes care of fetching the library code and making it available to the project. Integrating with RESTful APIs. Swift developers often need to interact with RESTful APIs to fetch or send data to a server. This is typically done using the URLSession class for network requests. Below is a simple example showing how to make a GET request to a RESTful API in Swift. The code snippet above uses URLSession to create a data task that sends an HTTP GET request to http://api.example.com/data. It converts the returned data into a UTF-8 encoded string and prints it to the console. Error checks ensure that we only try to process the data if no error occurred, and if the HTTP response status code is 200, which typically stands for OK. If the requested information is retrieved successfully, it can be parsed, e.g. using JSON decoder, and used within the app. Local notifications. Local notifications are a way to inform users about events happening within an app, even when the app is not in the foreground. In Swift, local notifications can be scheduled using the User Notification Center class. The code imports the User Notifications framework and sets up a mutable notification content object with a title and body for the notification message. It then creates a time interval notification trigger to fire the notification after a day, represented by 60 seconds, 60 minutes, 24 hours. With the content and trigger, it creates a UN notification request object, which is then added to the UN User Notification Center. If the addition fails, an error is printed to the console. Background execution. In iOS, executing code in the background allows your app to perform tasks even when it's not in the foreground. However, iOS is stringent with background execution to conserve battery life and maintain performance. To perform tasks in the background, you must explicitly configure your app and follow the guidelines provided by Apple. The provided code snippet configures background fetch for your iOS app. In did finish launching with options, we set the minimum interval for background fetches to the smallest possible value, which allows iOS to wake the app and give it a chance to update its content. The function perform fetch with completion handler is called by iOS when it's time to perform a background fetch. Inside this method, you execute the actual background task and call the completion handler with a UI background fetch result value indicating whether new data was fetched. Code signing and provisioning profiles. Code signing is the process of digitally signing your app to ensure that it comes from a known source and hasn't been tampered with. During development, Xcode automatically manages code signing with a development certificate. For distribution, however, you must sign your app with a distribution certificate and a matching provisioning profile. In iOS development, code signing involves two main components: certificates and provisioning profiles. A certificate is tied to a developer's identity, and a provisioning profile dictates what devices the app can run on, which entitlements are granted, and which certificate is used. Before an app can be run on a device or uploaded to the App Store, it needs to be signed with a relevant certificate. Xcode can automatically manage these profiles, or developers can manually manage them through the Apple Developer Portal. Building and archiving. In Xcode, building entails compiling the app's source code into an executable file, while archiving bundles that executable along with all of its resources into an archive that can be used for distribution on the App Store or other methods. In the context of Xcode, building converts your Swift code and other resources into a runnable app for a specific device or simulator. Archiving goes a step further, creating an archive.xarchive, which consolidates the app executable and assets used for beta testing via TestFlight, submitting to the App Store, or ad hoc distribution. To perform these actions, you would normally use the product menu in Xcode, selecting Build for building and Archive for archiving. These steps are integral to preparing your app for testing and release. Beta testing with TestFlight. TestFlight is a service provided by Apple that allows developers to distribute pre-release versions of their apps to beta testers. This helps in catching bugs and getting user feedback before the final release of the app. TestFlight can manage multiple builds and testers and provides analytical data to the developers. To distribute an app via TestFlight, you need to upload a beta build to App Store Connect, add tester information, and then testers can install the app via the TestFlight iOS app. TestFlight does not involve traditional code, as it is more about the process and usage of the TestFlight service. Therefore, the code section is not applicable in this context. To use TestFlight, you must first archive your app from Xcode, validate the build, and then upload it to App Store Connect. After that, you configure the testing options, invite testers by entering their email addresses or sharing a public link, and then they can begin testing the app by downloading it through the TestFlight app. App Store submission. The App Store submission process involves preparing your iOS app for release on the App Store. This process includes configuring your app's metadata, taking screenshots, and uploading your app through Xcode or the application loader tool. There's no specific code for submitting an app to the App Store. Instead, it's a series of steps in Apple's developer portal and Xcode. You'll set the version, build number, and provide assets like app icons and launch screens. Update your app's listing with descriptions, keywords, and screenshots, then choose pricing and availability. Finally, select Upload to App Store within Xcode's Organizer window after archiving your app build, then complete the submission in App Store Connect. App updates and maintenance. Once an app is distributed and available to users, developers must keep it updated and well maintained. Regular updates can include bug fixes, new features, performance improvements, and adjustments for new operating system versions. Regular maintenance ensures the app remains functional and secure. This concept does not typically involve code, as it is more about the processes and best practices. For app updates, you would modify your app's codebase to implement changes or improvements, recompile the app, and then go through the process of submitting the new version to the App Store. Maintenance often involves monitoring app performance, checking crash reports, updating third-party libraries, ensuring compliance with guidelines, and fixing issues as they arise. App Store Connect and Analytics. App Store Connect is a suite of web-based tools for managing apps sold on the App Store for iPhone, iPad, Mac, Apple Watch, Apple TV, and iMessage. As there is no specific code associated with App Store Connect, it's mostly about managing your app's presence on the store, tracking performance, and analyzing user engagement through analytics provided by Apple. While App Store Connect does not involve code, it offers analytics which allow developers to see how users find and engage with their apps. For example, you can track App Store impressions, user engagement, and demographics. These insights can help developers make informed decisions about app marketing and development strategies. Unit testing. Unit testing involves testing the smallest parts of an application in isolation, e.g. functions, methods. In Swift, XCTest framework is used to create and run unit tests. A good unit test is one that is repeatable, independent of any other tests, and provides a clear indication of what is being tested. In the provided example, we import the XCTest framework to use its testing capabilities and MyAwesomeApp module to access the application code that we want to test. We define a test case by subclassing XCTestCase. Inside our test case class, we create a test method testExample, which is automatically recognized by the testing framework due to its test prefix. We perform the actual test by asserting that a value 10 in this case is less than or equal to 100, using XCTassert less than or equal. The third parameter is an optional description that can provide additional information about the test condition if the assertion fails. UI testing. UI testing in Swift allows developers to simulate user interactions with the app's user interface programmatically. These tests are often written with the XCTest framework. UI tests can simulate taps, swipes, text entry, and other actions, and they can assert that certain elements exist or contain the correct content after these actions have been performed. The given code snippet is an example of an Xcode UI test case. It begins by importing the XCTest framework. A new test case class, MyUITests, that inherits from XCTestCase is created. Within the class, there's a test method testExample, which initializes the application under test and launches it. The test method then retrieves a button with the accessibility identifier myButton and simulates a tap action. After the button tap, it retrieves a label and asserts that the label's text content is Hello World. This ensures that after the button is tapped, the expected result is displayed on the screen. Test-driven development. Test-driven development, TDD, is a software development practice where test cases are written before any functional code is implemented. The workflow follows a simple cycle. Write a test, make it run, write the minimum code necessary to pass the test, and refactor the code to adhere to standards. This cycle is often summarized as red, green, refactor. In the given code, We first define a simple function add that takes two integers and returns their sum. Next, we create a test case math tests with a test method test addition. This method uses xc_assert equal to assert that the add function returns the correct result when passed two values. The process starts by writing test addition before the implementation of the add function to ensure the function behaves as expected right from the start. Debugging with Xcode. Debugging is an essential aspect of programming. Xcode provides powerful debugging tools integrated into its IDE, which allow developers to track down and fix their code errors efficiently. The example presents a function that causes an index out-of-range exception. Xcode can help identify this error through the use of breakpoints, which can be added by clicking the line number where you want execution to pause. Once a breakpoint is hit during debugging, you can inspect variables, step through code line by line, and evaluate expressions to understand what's happening at that moment in your program. Performance profiling with instruments. Instruments is a powerful tool for performance profiling in Xcode that helps to identify and analyze runtime performance issues and memory leaks in apps. It provides visualizations and details about memory usage, CPU activity, and other critical metrics. Using it effectively can help improve the efficiency and responsiveness of your Swift applications. Instruments doesn't involve Swift code directly. It's an Xcode tool that hooks into your running application. To use instruments, you'd build your application with profiling enabled, then select the desired profiling template, and the tool will collect the data while the app runs. You can analyze this data to spot issues like excessive memory use, slow code execution, or resource contention. The key steps would be selecting the right tool within instruments, like the time profiler for CPU usage, or leaks for identifying memory leaks, running your app, and interpreting the results to optimize your app's performance. Addressing memory leaks. Memory leaks in Swift occur when memory is not properly released, often because of strong reference cycles between objects. Addressing memory leaks is crucial to prevent your application from using more memory than necessary, which can lead to poor performance and crashes. To resolve memory leaks, you can use weak or unowned references to break these cycles, or use closure capture lists to specify how closures capture references. In the provided code, there are two classes, person and apartment. A person may have an apartment, and an apartment may have a tenant, a person. However, if both references are strong, a strong reference cycle will be created, and neither class will be properly deallocated from memory, leading to a memory leak. The tenant property of the apartment is declared as a weak reference, weak var tenant person, which prevents the strong reference cycle. When the person or apartment instances are no longer needed, Swift's automatic reference counting (ARC) system will deallocate them, provided there are no other strong references to them, thereby avoiding memory leaks. Exception breakpoints. In Xcode, exception breakpoints are used to pause the execution of code at the point where an exception is thrown. This allows developers to inspect the state of the app at the time of the exception, making it easier to find and fix bugs related to unexpected errors. Exception breakpoints aren't set in the Swift code itself. Instead, they are configured within the Xcode IDE. To set an exception breakpoint in Xcode, open the Breakpoint Navigator, Command 8. Click on the plus button at the bottom left, and select Exception Breakpoint. You can choose to break on all exceptions or specify a particular type, e.g. C++ or Objective-C exceptions. Once set, the debugger will stop your code whenever an exception is thrown, allowing you to examine the call stack and variables to diagnose the issue. Using console and debugging tools. The console and various debugging tools in Xcode are vital for diagnosing and resolving issues in your Swift applications. Using print statements for logging and breakpoints for stopping execution can give you insights into how your code is running. The print function outputs the string into the console, which helps track the flow of the app and the state of variables. The given code logs the value of a variable x, wrapping it in a string interpolation for display.